So electric motors. So all electric motors operate on the principle of attraction and repulsion of magnetic fields. One or both of the fields must be electromagnetic. So the minimum we'll have is one, but we could have two. And y'all know that light poles, what do? Now listen, magnets, like magnetic poles, what do? They retract or repel. So if I came over here and put a north up against a north, yeah, that repels. So the easiest thing is to take out some. So I got two magnets and they're hooked together. So I'm gonna come up here and put like magnetic poles. So this would be either north to north or south to south. I don't know what it does. And what I'm gonna do is I'm gonna come over here and just let it go. So it definitely repels, right? And then unlike poles do what? They attract. So somehow I could come up here and have this feature and cause one of the poles to move, then the other poles would follow it, right? You understand that? It would lock in. So up here, this might be repelling. If it's repelling, it would push this one away, and then we'll be attracted on the next one, and we make one of the magnetic fields. Somehow we make one of the magnetic fields move. And then, of course, make it move. So one of the magnetic fields is going to be somehow switching, and then the other one is going to be stationary. So technically, in DC motors, it's a little different, but in AC motors, and you'll hear people misname this all the time. So the motor, besides for the frame, so the frame is what holds everything together. So we're going to have one field, which is going to be stationary. It's going to be mounted. On AC, we refer to this as the stator. And then we're going to have another magnetic field that's going to spin. And on AC motors, we call this the rotor. And this is where your bearing is going to come into place. Your bearing is going to be on your rotor, right? You understand, on the motor. And what we do is somehow we make these magnetic fields shift. And of course, and one of them is going to be electromagnet. Y'all okay on electromagnets? Okay on those? I think I've got electromagnet in my computer bag. I'll have to go get it and show it to you. So an electromagnet, anytime we put current flow through a wire, it creates a magnetic field around it. And if it's DC, then the magnetic field will come up and build up and it'll stay out there, right? Understand that? And if we do the same thing and we do a wire right next to it, then what happens if it's moving in the same direction, then they combine. So what we can do is we can come over and put a bunch of loops of wire, and they're all looped in the same direction, and then each little magnetic field would combine, and we end up with a stronger magnetic field. And then, of course, we'll concentrate it with some type of metal. We'll concentrate the magnetic field being created by the electromagnet. So one of the fields has got to be electromagnet, or both of them can be, and that's what we're going to look at. So we have two categories of motors. We have DC motors and we have AC motors. Inside our DC motors, we have what we call a shunt motor. And we have what we call a series motor and a compound motor. And then we'll have one that will fall in this category right here, which would be a permanent magnet motor. Then we have what we call a stepper motor, which we've got one of these over on the armored control line. And then we have a brushless motor. We don't have any of those. Yes, we do. I'll have to find one though. Single phase motors, y'all probably got a bunch of these around your house. We have capacitive start, capacitive run, split phase, and shaded pole. Three phase motors, we have Y wound, delta wound, we have Y delta and wound rotor, which you don't see much anymore unless you get around a train. And then we have synchronous motors, single phase and three phase motors. We okay so far? So this is a DC motor. So a DC motor consists of a couple of parts. We have a magnet. So this guy right here, this is a permanent magnet motor. That these are all the motors on the manufacturer lines are permanent magnet motors. All the motors except for your starter on your car, the thing that actually starts your car with that switch. These are electromagnet motors. So, permanent magnet motors. So the ones that raise your windows up and down, the ones that lock and unlock your car, the ones that run your windshield wipers, these would all be permanent magnet motors. When we get into industry, these are not really high horsepower motors. They don't create a lot of torque. So if you get into industry, they'll run into these other parts. But we have the same thing. We have this right here can either be a permanent magnet or it can be an electromagnet. So in industry, high probability it's going to be electromagnet. But like I said, all of them that we have here is permanent magnet. And then we have, and we call it, by the way, on DC, you'll hear a lot of people call this the stator for stationary, but technically in DC motors we call this the field. And then you have a rotating magnet. This will always be an electromagnet. And then it's technically on DC motors called the armature. On DC motors, if I said that right. But if my boss called it the rotor, I would say that. Now, what we're doing, and I've got a really good video I'll have to show you. I don't know if it's going to play or not. Let's see if we can see. See, I can see basically how these things work. I wish I had it already loaded up. So he did a really good job on his. And you saw how the DC motor works. So what we have is we have an electromagnet that is it's the rotor, right, or the armature. And then on these motors, we have a permanent magnet that it's working again. And the permanent magnet and the brushes are mounted 90 degrees apart. So if this is a north and this is a south, and this is always a south and this is a north, then as soon as it turns, then the commutator switches it to keep the north and south in the same orientation. And to reverse it, how would y'all think we would reverse the motor?
Swap polarities.
To the what?
To the opposite polarity.
Well, we got the parts. So when you say swap the polarities, here we got a permanent magnet, and you're right. But we swap the polarities to the armature, and we'll talk about why we don't swap it to the field, even if it's an electromagnet. So yeah, that's. So I shut off my PowerPoint, so I need to find them again. And we have different methods that we use to swap that polarity, and that's one thing we need to see is how do we reverse these motors. So all the motors are reversible if you know what you're doing. Now, most of your motors in your house, though, are wired to run in one direction. And you would literally have to take them apart and rewire some things in there to make them switch directions. So these are the brushes, and then we'll have a copper wire that's embedded into the brush. And that's what you gotta do. DC motors require maintenance. Because these brushes are running, so we got brushes and riding on something that's in motion, which means they're gonna wear down. And if you let that copper wire that's got a plate in here come in contact with your armature, with your commutator, it's gonna mess it up. I wish we was over there in the other lab where you could actually see a motor that's just messed up because I let that happen. Brushes, carbon blocks with copper wires attached, use to transfer current from the power source to the commutator, normally reversed by reversing the voltage on the armature. Now, what determines the strength of the magnetic field, of course, is current. But we know current and voltage are directly proportional. Now, these things work. It's really, really neat, is that you notice when you put his voltmeter on there and he spun it, the armature created a voltage. And we call it a counter EMF. So what happens when we start off, the rotor is no speed at all. And we come over here, we have a magnet. So what do we need to create an electromotive force magnetically? Anybody know? What three things? Magnetic field. They got a magnetic field. Well, let's do the next one. We got to have a conductor. And then three, we got to have relative motion. And what determines the strength or the amount of EMF we get? Strength of the magnet. We can't say that anymore because we have what we call rare earth magnet. And you'll get a little old magnet about that big, and that sucker will be strong. Strength of the magnetic field. 2, number of conductor loops. Right, space. And 3 is the speed of the motion. So here we got magnets. We got a bunch of conductors inside this armature, and this thing's in motion. So this is going to induce a voltage back into the armature that's opposite of the applied voltage, and we call it a counter EMF. So what happens, you start off your motor still. It's got current on it, like this might be a north and this might be a south, and this right here might be a south, and this over here might be a north. We put power on the armature, right? North, south, this thing here spins. And it's got a lot, the only resistance in the wire, the only resistance of and then the current in the armature keeps going down because the counter EMF is taken away from it. But so we start off with a lot of torque, which is what you want on the motor. But as it comes up to speed, what would it do? The actual current in the armature starts dropping down. How fast will it run? Well, it'll run as fast as it can to produce the torque that it needs to torque to turn the load. So that's what sets the speed of a DC motor. Because if I came over here, and so we started out, we might get like 1 amp through the rotor, and then it starts going, 1 amp, 800 milliamps, 400 milliamps, and then how much does the motor pull? Well, it pulls enough to create what it's rated at its rated speed, and we call it a counter EMF. So we got everything we need. We got turns of wire and everything, but it's crossing them and producing that counter EMF. So that's what controls the speed of a DC motor. If you apply more torque, if it requires more torque, it slows down. Counter EMF goes down. Current in the armature goes up, causes the motor to produce more torque. Are we okay? That's what he was talking about. He actually spun it, and he could see the thing worked. In fact, we can run DC motors as generators. So this is the types of DC motors. We have what we call a shunt motor. So a shunt motor uses an electromagnet as a field, and we don't have any around here. We got some over in the. And then of course this is an electromagnet. This is stationary, and of course this is rotary. This is representing the brushes transferring the current into the armature. So what happens if I come over here, let's say it's rated at 120 volts DC. Then I'm going to put 120 volts here. And then we're putting 120 volts here. Of course, the motor will come up and start running, right? Counter EMF will start being produced, and it will come up to a certain speed, whatever speed is required to produce the torque. Well, let's say I come down here and this voltage drops down to 115 volts. Well, you'd think the motor would slow down. Well, what happens is we come over here and put this over here. We come over here, but we're also decreasing the strength of the field, which means the motor's going to have to run faster. Instead of slowing down, it's going to have to keep up or produce enough counter EMF to take away from that right there. So the advantage of a shunt motor over a range, it tries to run at the same speed, even though the voltage is changing.
You can run lower volts.
You could, but you would have to change it. You would have to change.
The field.
Yeah.
Make it bigger.
Well, we could. No, and that's a really good point. What we're doing is we got to understand, and that would be more in this one. This is what we call a separate excited motor, and we'll talk about that on this one. So notice on this one, the actual field is separated from the armature. Over here, the voltage on the field and the armature are always the same. So if the winding, if I put a lower voltage on here, we're decreasing the strength of the magnetic field, which means the motor's got to run at the same speed to get that torque. Does that make any sense? I don't know if I'm saying that right or not. But over here, I could come over here and I could have a different DC source. So I could come over here and have a DC source running the field, and I could have a completely different DC source running the armature. So if I leave the voltage on the voltage, which is proportional current, if I leave it the same, let's say I come over here and this is 12 volts, and then I come over here and apply this 1 volt, then the motor would come up to speed until it cancels out 1 volt. If I raise this up to 2 volts, then the motor's got to run a little faster to cancel out 2 volts, right? You understand? If I come over, so what we're doing is we're controlling the speed with the armature. So the higher the voltage on the armature, the faster the motor will run. So the higher the voltage on the armature, the faster the motor will run.
Well, with the other one,
It tries to maintain the same speed as long as it can reduce. So the speed of the motor is set by the strength of this field. So if the strength of the field goes up, what would you think the motor would do?
increase the speed.
Well, you think about it. It's creating what determines the amount? The strength of the field. So over here, if I come over and increase the field, then that's going to produce more counter EMF, and it's going to cancel out some. So if on a separately excited motor, if I increase the strength of the field, the motor slows down. Not the armature, the field. Because it works on counter EMF. And what determines the amount? The strength of the field right? So the formula would be set by speed, would be set by the armature voltage minus the counter EMF. Now these will never actually cancel each other out because you gotta have current flow through your armature to create torque. So that means if I come over here and put 12 volts on there, the motor starts off counter EMF is equal to 0. So now the armature is going to produce enough current for 12 volts. As soon as the motor starts spinning, this might go up to 1 volt. And what's going to happen? The motor's still got enough current in the armature, right? You understand, to keep spinning up, but it's not going to be as fast. Now, when I get up to 12, there would be no current flow through the armature. The armature would have no magnetic field, and we wouldn't create any torque. So that never happens because we got to create enough torque to run the load. So the motor would run at the speed that's required to run the load. But if I come over here, what determines the counter EMF is the strength of the field. So I come over here and I increase right here. The strength of this field goes up, which means this motor is going to produce more counter EMF. It's going to hit counter me up 12, 12. It's going to say, hey, I need to slow down to create any torque, right? So it'll slow down. So on a DC motor, if you control the strength of the field, the speed runs opposite of what you do on the field. If you increase the strength of the field, then the motor slows down. If you decrease the strength of the field, then the motor's got to run faster to cancel out the applied voltage. This one, if we decrease this, we decrease that. So it's going to try to run at the same speed. So if we decrease this one, we decrease that one, and the counter EMF still works, right? You understand what I'm saying? So if this one drops down to 115 volts, this will drop down to 115 volts, and the motor's going to run about at the same speed. So a shunt motor has really, really good speed regulation. Even though your input voltage is varying a little bit, this guy here wants to run at the same speed. A separately excited motor, we can control the speed by either changing the voltage to the field or changing the voltage of the armature. But if you change it to the field, it works in the opposite direction. If we increase the strength of the field, the motor's going to try to produce more counter EMF, which means it's going to have to slow down, right? You understand that, for a different speed. But the advantage of playing around with the field is the torque of the motor. So if the field strength goes up, then torque goes up. T-O-U-R-Q-U-E. And if the field strength goes down, then torque goes down. But if torque goes up, speed's got to go down, right? Or vice versa. But if I decrease the strength of the field, then speed's going to have to go up to produce the same counter EMF. And this is what you'll run to more in it. Well, that's not true. This is just a way that you can control too. Changing armature current changes speed in the same direction. Changing field voltage changes speed in the opposite direction, but increases torque in the same direction. These are expensive to control. So instead of trying to control one thing, you're trying to control two. They had these at US Steel. When you started off, because the size, so they had a motor that was pulling a strip, and the strip was coming off a roll. Well, the problem is that the roll starts off this big, and you want it to run at the same speed. So what was happening is it started dropping down. It required less torque, but you wanted it to run at the what? At the same speed. Yeah, well, it wouldn't run it. So this was the galvanizer line, and so they had a big old vat of zinc, and they would run the strip down through the zinc and coat it. Well, to get the right coating, it had to run at a very precise speed. But what was happening is the rolls would start dropping down. This motor over here is running, and it would feed off faster, right? You understand, because it's getting lower. So what they wanted to do is they wanted to maintain the same speed and change the torque because it required less torque. So on those motors, on number 4 galvanizing lines, they control both the torque and the speed. So if the speed was staying the same, but the size of the strip was going down, they could control that. But it's not an easy thing to do, and it was a very expensive drive system. And the problem is it had to run at exactly the same speed. This is what we've got. We got permanent magnet motors used on both Amatro and the MTS line, which is the Festo line. Speed change with armature current, reversed by reversing the armature connection. This has got a good speed characteristic, good starting torque, but it's a very, very low horsepower. These are your very low horsepower motors. And in fact, the motors that they use over there, these are actually Fusion motors. So if you look at the motors on both the Festo line and the Amatro line, what you'll see is they'll look like this. Well, they won't have disassembly, but I can come over here and I can spin this motor freely. By the way, this is a quadrature encoder, but when I come over here, I can't turn this because it's going through a gearbox that does what? Reduces speed, but increases torque. So the problem is I'm going backwards. So even though I can spin this guy here like nothing, I can't spin the motor from this end because I cannot create enough torque to get through the gearbox. This right here is a 65.5 to 1 gearbox ratio. So that means for every 65.5 turns this guy makes on this side, this guy on the end only turns 1 revolution. But it's at a lot higher watt. Speed goes down, torque goes up. So this guy over here, man, it's moving. By the way, this is a quadrature encoder. This does it a little different than most of them. You can actually see the 2 slots in the encoder itself are offset by 90 degrees. So here the actual photo transistors are lined up vertically. But if we're turning this way, then the top one would pulse first. If I turn it this way, then the bottom would pulse first. So this is actually a quadrature encoder. So that's permanent magnet motor. So they're compensating for the lack of torque by using a high-speed motor through a gearbox, right? How many gears in there? I have no idea. It's all filled up. But it's a 65.5 to 1 ratio. This is a series motor. So these are the only motors that's on the Amatro line. And except for your starter, which is one of these, your starter on your car is one of these. So your windshield wipers run off a permanent magnet motor. Like I said, your door locks run off a permanent magnet motor. Your windows that raise and lower the windows run off permanent magnet motors. If you got an electric seat that you can adjust features of your seat, it uses permanent magnet motors. But it probably goes to a gearbox, right? This is what your starter is, and most hand drills are series motors. So what we do here is we actually put the field in series with armature. So the strength of the field is set by how much current flows through the armature. So if the motor tries to slow down, then it's producing less counter EMF, which causes the current to go up, which causes the current in the field to go up, which creates more field strength, which creates more torque. So these guys have very, very poor speed regulation, but they create a lot of torque. And you can see this on, if you've got a hand drill. So you got a hand drill, you hold it up in the air and it runs real fast. As soon as you hit the board, what's it do? Slows down. But the torque goes up because the field the field current goes up, which produces more EMF, which causes the thing to produce more torque. And some of these motors, guys, they'll jerk right out of your hand. This is the starter on your car. Your starter uses the series motor on your car. Creates a lot of torque, not really good speed characteristic, but creates a lot of torque. Great starting torque and run torque, very poor speed regulation. Universal motors, by the way, these guys, the field is very few windings. So we do have a problem with putting AC on this thing. It's called X of L equals 2 pi FL. And this is the opposition of a coil of wire. And the more turns it has, it would cause L to go up, which would cause with frequency. This is frequency. But if you got very few turns of wire, then your L is almost nothing, which means some of your series motors will run on AC or DC. And these motors are called universal motors. So that's usually what your vacuum cleaner is. If you got a vacuum cleaner, or if you got a compressor, a small compressor, it's probably got a series motor in it, and it's probably running off AC. So sometimes they refer to these as universal motors, which is what the guy that did the video said. This is the only one you can do that. And the reason we can do that is the L of the coil is so low that it has hardly no effect with frequency, as long as you don't let the frequency get too high. Used in applications that require extremely high starting torque and run torque. Power hand tools, combustion engine starters, vacuum cleaners, and small compressors. We use this. A compound motor. This is what they use in the industry most often. High starting torque, good speed regulation. We have what we call a cumulative compound, which means the series field and the shunt field are wound in the same direction. Series field aids the shunt field, high starting torque but less speed regulation. Then we have a differential compound, which has good speed regulation but less starting torque. Operates at a constant speed. So these are most of the motors you'll run into in the industry. We okay? So speed control, armature voltage with armature, increase the voltage on armature, speed increases, voltage decreases on armature, speed decreases. Normally used because of the speed. The problem we have with using a shunt motor is it's trying to make now what determines the amount of counter EMF would be the strength of the field, right? Now these are DC, so the problem is in the motor, these fields are actually wrapped around a chunk of metal to help concentrate it. If you expose metals to a magnetic field, they try to magnetize, right? So I come over here and I put 120 volts, let's say I put 12 volts on here, and we have 12 volts over here. And let's say the field opens. What would the shunt motor do? Well, it works off counter EMF. We do have a little bit of magnet over here, but it's got a real small magnetic field. So what happens is the strength of my magnetic field goes down, which means the motor is going to try to run faster to create the counter EMF. So the problem with the shunt motor, if the field opens, there's a high probability that the motor will run away and sling itself apart. We had this happen on a motor that was, and we never could figure out what was going on with it. When I left, they were still having problems. But they had a big old 200 horsepower motor, which probably had a diameter of maybe a yard, or I'm sorry, about 2 or 3 yards. It's a big old motor. And it would sling itself apart every once in a while. And they had overspeed indicators, they had fill loss indicators on it that was supposed to shut the motor off. So normally on these big old motors, you'll have a fill loss, so you'll have a current sensor in here. And if this current ever drops to zero, they'll kill the motor. Because if it's a shunt motor and it runs off counter EMF, so it sets the field right here. So this sets the speed. Armature minus counter EMF. And then it's for torque, right? Well, if the counter EMF drops to almost zero, then the motor's just going to speed up. So this is a big problem we have with shunt motors, is if you lose the strength of the field, the motor can run away. So, but if you lose the connection on the armature, the motor will stop. So, if I'm going to change something, if I'm going to put a control system, if I'm going to control the speed of the motor, odds are we're going to put it in the armature, because if something goes wrong with the voltage or something going to the armature, the motor will stop. If something goes wrong with the voltage going to the field, the motor could run away. So when we reverse a DC motor, we could reverse the connections on the field, and the motor would reverse directions. But if my reversing circuit failed, then the motor could run away. So normally when on a DC motor, if we're going to control the speed, we control the speed with the armature. If we're going to reverse the motor, we're going to reverse the armature. So instead of doing it one way on one motor and another way on another motor, it's just a common feature. So field, voltage increases, speed decreases, and torque increases. Voltage decreases, speed increases, and torque decreases. Not normally used because if the speed control circuit failed on a shunt, separate excited, or compound motor, while in operation, the motor may run away. So instead of doing it this way on one DC motor and this way on another, we do it the same way. By controlling the what? Johnson. So that's what I'm doing on this little motor right here. So this is a permanent magnet motor, so I can't control the speed with a permanent magnet, right? Understand? So all I'm doing is controlling the speed. And how fast does the motor run? Well, it runs at the speed where the applied voltage is subtracted by the counter EMF voltage, and then, of course, that's the speed it runs at, plus torque. So they'll never be equal to each other. That makes sense? So very simple to do. And look how precisely I can control the speed on this thing. And this is still one of the biggest advantages of a DC motor, the control we have over the motor. So these are some of the ways that we control the speed. So these are, by the way, these are what we call bipolar transistors. And these work like current valves, guys. So the more current I put into here, then it controls the valve. So I might be putting maybe 100 milliamps in here, and what it does, it might be controlling a current of 2 amps. So these are kind of like everybody's got faucets in their house, right? And where you can control the water. Have you ever tried to control the speed of the water with your hand? Does it work very well? Just pushes it out of the way, right? But yeah, I can take that little old valve that's got a stem on it about like that, and I can control the speed of the water with very little torque. So this is what a transistor does. It gives us a current gain. It's a current valve. So what we do is we put a very little bit of current into this lead right here we call the base, and we get a big current gain out of it. So we're controlling the size of the valve with this lead right here. And then we're taking that 1 amp or that 2 amp and pushing it into another valve. So this might be 2 amps over here, and this might be 20 amps over here. And then this is what's actually feeding our DC motor. So what happens is if I come up here and change this voltage, the more I move it toward 12 volts, the motor runs faster, and the more I move it toward 0 volts, the motor runs slower. Now the problem is that these guys right here drop a voltage. If they drop a voltage, then power is equal to V times I. So that means if my control voltage is 12 volts, and I turn this on enough if I turn this on enough to get 3 volts right there, then I'll get 3 volts right there. Well, what it means, this guy right here is dropping 9 volts at 2 amps. So that'd be 18 watts that thing's dissipating. This guy right here would be dropping 9 to 3 would be dropping 9 volts, but it's going to be 20 amps. So that thing would have to dissipate 180 watts. So what they wanted to do is come up with a method where we didn't use these linear switches, that we came up here and we used a method where we could either turn these things on or turn them off wide open. So if this guy right here drops 0 volts, then the power it dissipates would go to 0. So the technique we use most often now, so this is actually using a resistor, and that resistor would really get hot. But what we use now is we use a technique called the pulse width modulation. And I usually hook up a motor to this, guys. If I got time, I might do that. Rheostat, but it's a resistor. So the problem with resistors is if they drop a voltage and they have a current flow through it, then they get hot. And that's why resistors are rated in watts, right? You understand? So like I said, if I was to come over here and I put 10, if the resistor was dropping 10 volts, and of course, let's say over here I have 20 volts and over here I have 10 volts. Well, the resistor's dropping 10 volts. So if it's dropping 10 volts and it's conducting 1 amp, that means the resistor itself is dissipating 10 watts of power. So a while ago, I had my transistor, and I said, okay, up here, up here I have 12 volts, down here I had 3 volts, and I said there's 20 amps flow through it. Well, what the voltage drop be? Well, the voltage drop is going to be, 9 volts. So now that P is equal to V times I, so that thing right there would be dissipating 180 watts. Okay. But if it was a switch, so it's a switch, and I got this over here on my motor, and this is the symbol for an armature. So if I was doing this, if I was controlling the speed of my armature, so let's say I was controlling the speed of my motor with a rheostat, which can be done. It's a DC motor. But the problem is if I'm putting 12 volts on here, and I come over here and I adjust this to get 3 volts, and the motor needs 1 amp, then that means that rheostat is going to have to dissipate what? 9 watts. You understand that? But I come over here, and I come over here. Let's say I put 12 volts over here. Well, the switch is open. How much current flow is through my switch? None. How much current flow is through the motor? None. Right? Okay. I close it. So let's say there's 3 amps. How much power is the switch dissipating? None. Because it's dropping 0 volts. Now, of course, the current would go through my motor, right? You understand? So what we're doing is we come over here and we're putting pulses on this thing. And the motor is sitting there, and we put voltage on it, it starts turning. We take it away. Well, it's already what? It's already turning. Then we put voltage on it again. Then we put voltage on it again, and then it's spinning. It's going to average this out, guys. And you can actually see the average. So this one, if I hook this up to a DC motor, what would happen is if I would come over, now there's no such thing as a perfect transistor switch, so the switches still get hot, but they don't get near as hot as, so if I hook this up to a motor, and unfortunately my little function generator won't put out enough current to run that motor. I had a little tiny motor. But what would happen is I'd come over here and I'm not changed. So here it's on, so this means that my motor would be getting full voltage. Here it's off, the motor would get 0 voltage, but the motor's already spinning. So the motor would run at this speed right here. Whatever 3.6 volts cause that motor to run, that's the speed that motor would run at. But what I can do is I'm changing what we call the duty cycle. So here the motor would do what? Slow down. Here the motor would do what? Speed up. So here, if this was a 5-volt motor, it would be running wide open. Don't care. You don't care what it's getting. Right? You understand that? And this is the method that's most likely used now. In fact, programmable logic controllers, newer programmable logic controllers will do this. It's called pulse width modulation. And all we're doing is we're either turning those electronic devices on, or we're doing what? Turning them off, and the motor averages it out. And we can precisely control the speed. And you can actually see the voltage. Well, I had a little old tiny motor that the function generator would run. This guy don't put out enough voltage to run this motor right here. This motor. But I can hook up a transistor and do that for you. We call it, so you can actually see the average DC. So we can control the speed of the motor precisely using what we call pulse width modulation. And this is showing me my average DC right here. But notice the frequency is not changing. So if I looked at this leading edge and this leading edge, it never moves. So that means the time for a cycle never changes. Are we okay? Reversing. Reverse the electrical connection on the armature and not the rotor, not the field. This is the normal way to reverse a DC motor, because if reversing circuit fails, the motor will stop. Reversing the electrical connections on the, I'm not going to say you're not going to run it. What we're talking about is the normal way, right? You understand? So if you get out there to the company and they reverse the field, you're not going to say, well, Rick said you couldn't do that, because that's not true. You can. It's just more dangerous to do it that way. Reverse the electrical connection on the field and not the armature. Very seldom used because a shunt separately excited and compound motor may overspeed if the shunt field connection is lost due to reversing circuit. The motor will not reverse if you change both fields. So if you change both fields, I don't know if anybody, are y'all raising y'all's hands or something? I can't see y'all guys. So if you reverse both fields, if you reverse the field on the rotor or the armature, and you reverse the field on the, the connection, the motor won't reverse. It'll run in the same direction. Used to in motor controls, we'd go over there and do that. And I say, what's going to happen when we reverse the wires? They'll say, well, it's going to reverse, but it don't, because I'm doing the field and the armature at the same time. So what you have to do is you have to change the relationship. So if this is a north-south and this is a north and this is a north-south, then the motor would repel from the north, y'all can't see me on home, and move to the south, right? You understand? If you reverse both of them, then it's still going to turn in the same direction, because it would still repel and retract. So what you have to do is you have to leave this one alone and do what? Maybe reverse the field or reverse the armature. And of course, the most popular way is the armature. So here's some reversing circuits. and one they didn't show, or I think it's on the next slide. So here they're electronically reversing it. So they would turn on this transistor and they would turn on this transistor. And here it would cause the current flow to go through the motor that direction. Or electronically, I would turn on this transistor and this transistor, which would cause the current through the rotor to change.
So that way it wouldn't matter which one you reverse, I guess, because there's only one way to reverse it. It's not like reversing the armature. So
Well, we're reversing the current flow through the armature. So we're not disconnecting the motor. So I guess I should have rephrased that. We can reverse the current in the armature or we can reverse the current in the field. If you reverse the current in both of them, it runs in the same direction. So notice if I turn on, if the electronics turn on these two, so they're staggered. So either these two are on or these two are on. So if I turn these two on, then the other two would be off. So this would be on, this would be on. Then the current flow would be what? Would be through here. Then the current flow is in that direction. And then it would go back up to this one. So now the motor would run in one direction. Is it reverse or forward? We don't know. Those are relative terms anyway. We probably could say there's a rule. I don't know if it's the left-hand rule or the right-hand rule where you can figure out which way a DC motor will turn depending on the current flow. Now I'm gonna leave this up there so you can make sure you understand this. So I'd come over here. I'll turn this one off, and I turn this one off. And then the motor could stop, right? Then I would come over here, I'm gonna turn this one on and this one on. And now the current flow would be what? Up through this one. That one's off, so now it's going in what direction? That direction right there, up through here. And what would it do? It would reverse. But we're reversing it electronically. We're not actually switching the leads. That makes sense? So this is the same thing, but this is using field effect transistors. But either what? Either this one's on and this one's on, or this one's on and that one's on. Now all the ones, we got this circuit right here. So here what we're doing, so we could technically do it like this too. So I could have, if I had a plus 12 and I had a minus 12, and then I had a switch that went like this, and then I put my motor over like this. So that's a symbol of armature, by the way. And then I hook this to common. Then if I flipped it up this way, the motor would run in one direction. If I flipped it down, it would run in the other. The problem we have with this, especially on big motors, so anything that's in motion wants to do what? Stay in motion. So here I got this big old motor, and it's running in one direction, and I flip that switch, and it's going clockwise, and I'm telling it to go counterclockwise. And what's going to happen? Hey, anybody have a ceiling fan? Hey, anybody have a ceiling fan? What happens when you change directions while it's running? Does it reverse instantly? What do you hear? It goes. So what it's doing is trying to pull all that torque to do what? To actually change directions. We call that plugging. It's not real good on a motor to plug it because it makes it pull a lot of current while it's trying to change direction. So what we like to have, and that's the same thing with this guy right here. So this guy right here, they put it on forward, and the current flow would be one direction. They flip it over to the other one, the current flow would be the next direction, but the motor would plug. So plugging means changing the direction of the motor without coming it to a complete stop. So if you want your ceiling fan to last a long time, you need to turn it off and let it do what? Stop, and then flip directions and turn it back on. So you'll burn it up. This is what we call an H control, and this is what they use on the Festo line back there. We have two relays. And notice reverse and forward. So what I can do is I can close the reverse, and the current flow would be up through here in this direction. I could open the reverse, cause the motor to come to a stop, and then I could close the forward. So the advantage of this is, plus we're using relays, but the advantage of it is we can prevent plugging of the motor. That makes sense? So,
That's correct.
yes,
Is there a way you could wire one of them up to be like a speed limiter?
not on this
Like
one.
you have like,
This is basically what we call just a reversing circuit. You can see why it's called a H control, because it looks like when we draw it, we usually draw it in the shape of an X. I mean H. So if I wanted it to not overspeed, then basically the only circuits that I've seen for overspeed control is one of them that we had out of U.S. Steel. We had a centrifugal switch on the rotor. So it's a centrifugal switch. So when the motor got up to a certain speed, the switch would open. We could come in and we could maybe put a tach generator on it and then kick it out when it got up to a certain speed, or a speed indicator. We could do it electronically. This right here doesn't control the speed. All this does is control the direction of rotation.
okay.
That answer your question?
Yes, sir.
Yeah. So we've got this on all the motors on the Festo line. We don't reverse, but I think it's it's module 2. If y'all working on that, we've got that carriage, and of course the carriage moves this way, and then it comes back. So that means somehow we're reversing the direction of that motor, and we got two. And then what we'll do is I'll come over here and put a normally closed contact and call it forward. And then I would come over here and do the same thing on my reverse. So what I do is I would put on my forward, I would put a normally closed reverse contact. And what this would do is this would, if I have the forward energized, then the reverse cannot energize. If I have the reverse energized, then the forward can't energize. And this is called an electrical interlock that we normally put in these circuits just to prevent that from happening. The problem we have, though, is that most of your relays, and I'll have to show y'all this, the other group, when y'all come in, it's got a mechanical override on the top of them. So what I can do is I can literally come in and I can push down on that thing, and it would cause the contacts to close. So if I was to come up here and I was to push down on both of them, then I've got a big problem. So what we do on this one, when I'll show y'all this on class, is we got what we call a mechanical interlock that goes between the two. So these right here are mechanically interlocked, which means I cannot even push them in at the same time. So normally on these things, since if both these relays come in at the same time on these H controls, you would have a short circuit. Then what we do is the best thing to do is put both electrical interlocks and mechanical interlocks. And that way somebody can't screw up. So the electrical interlocks prevents the programmable controller from this guy writing programs on the program controller and accidentally bringing those two relay coils in at the same time, which would be, well, this prevents that from happening even if they screw up on the program. The mechanical interlock prevents us from going over there and doing a mechanical override with pushing the buttons on the top and causing these two things to come in at the same time. So the best thing to do is to use both if you can. The Festo line has no reversers on it. The Amatro line's got two. One of them is the carriage that moves, where it checks the height, and then the other one is what transfers the carriage from the robot station over to the sorting station at the very end. And you'll see both of those have these mechanical interlocks on it. I'll show it to this class, but I'll show it to y'all when y'all come in on Tuesday, so you'll need to remind me of that. So this is probably the most popular way, is using relays, and then normally we control the relays with a program controller. And then, of course, we use, when a good programmer will put those electrical interlocks in there just in case they screw up on their program. And then when you buy the relays, you need to get those mechanical interlocks also so people can't go out there and force them. And you'll see me do that. So normally when we our ultrasonic sensor is out of calibrate. We noticed that the other day. I've forgotten who was programming. I think it was you, Jeremy. And when I put the module through there, I think, Jeremy, that was the one you was working on. When we put the module through there, it was supposed to reject. We have one of our blocks is deliberately too short. And so what should happen? It should reject that, but it didn't. It passed it through. So that would tell us that this thing right here is what? It's out of calibrate. So, but when we calibrate it, we can't do that with the PLC because the PLC is going to run it till it hits the limit switch, or it's going to run it back till it hits the limit switch. So what we do to position it is we use the relays, and we push it and bring it out till it's under the ultrasonic sensor, and that's where we calibrate it. So that's one of the things we're going to have to do, calibrate that when we put the line back together. And we might let each group do that. This is a stepping motor, and I have a stepping motor here, but my program, I can't find my program that runs it, so I'll have to see if I can find that and show that to you next week. But a stepping motor is a motor, I don't know if I have an animation on it or not, but yes, here I do. So what we have is the rotor on the stepping motor is permanent. It's a permanent motor. It's a permanent rotor. And what we do is we switch the outside field so this thing moves in steps. And the steps are really, really, really precise. So, and what you have is so the stepping motor I have over here, it's 100 steps per revolution. So that means each step would be what? It would be like 3.6 degrees per step. So instead of telling this thing to rotate, we tell it to move in steps. This is the motor that's on the carousel, the thing that moves around. This is the motor that's on there, and you could actually hear it when it moves. It sings at you. You ever notice that? And now that's what it's doing. It's stepping it so fast that it's singing at you, which is pretty neat. So these are stepping motors. What's nice about stepping motors is that they're so precise. If we can find a zero spot, if we can reference a zero, so we'll go over there and look at the carousel, and you can see that thing find zero. It actually comes up and finds zero. And then from that, if it's got 100 steps, if it's got, let's say it's got 360 steps, just for 360 steps, then if you wanted it to move 90 degrees, you would send it 90 steps. And it would move exactly 90 degrees. If you wanted it to move 180 degrees, you would send it 180 steps. So these things are really, really, really precise. These are used a lot on printers, so that's what's actually controlling the head on your printer. And you don't even, you can hear it well, there's two things you hear sing on a printer. You hear the, little piezoelectric guns shooting the ink, but you're also hearing the stepping motor step it to each spot where it shoots it. So that print head actually stops, shoots the ink, and then moves to the next print position because it's using a stepping motor. But once we find zero, then it's what? Then we just send it steps. We send it pulses around this field. And so I got a setup on this, and I'll try to get that working and show y'all that. It's really neat. This is half stepping the motor. So if you half step the motor, if you got what we call a 100 step motor, you can actually get 200 steps out of it by the way you rotate the fields, which is really neat. This is a brushless motor. This is used a lot. A lot of hand drills are going to this. The problem we have with hand drills, most of the time they use a series motor and they have brushes. And what happens when the thing runs, if you ever looked at the back of your hand drill, it's got grooves in there where it spins, it cools it down, you see the arcs in there. So most hand drills, you don't want to use those in gaseous environments, right? You understand that? So there's a lot of companies like DeWalt and it's moving over to this brushless motor. A brushless motor works a lot like a stepping motor, but what we do is we come over here and we rotate the field in here. And then the rotor is actually on the outside of the motor. And we've got one around here somewhere. I'll try to find it, y'all. So the rotor is on the actual rotor is on the outside, and it's a magnet, and it's what's actually spinning. So normally the rotor is where? Is in the center. But here on a brushless motor, the actual rotor is actually the outside. And I'll see if I can find that. These things don't create gaps. They don't create arcs. So they're biggest advantage. Yeah, but they cost a lot more. If y'all ever buy, if you go and buy a DeWalt and it's got a brushless motor in it, and they're a lot quieter too. If you got a fan inside your computer, it uses a brushless motor because these regular motors, they create a lot of electromotive interference. Okay, guys, y'all take a break. About 10 minutes, right? I need about every hour. So we really need to get through with this today. So Bernard left. The problem, why these are more expensive is that the rotation of the internal field has to be controlled electronically. So this takes a lot of electronics. So some manufacturers are actually putting these brushless DC motors into their hand drills. Now they got to have a lot of gearing available. So they don't have to have near as much gearing. I couldn't find my disk drive, guys. I wish I could. My floppy disk drive. I got an 8-inch floppy disk, and we've actually taken it apart so you can actually take the brushless motor apart on them. But I can't find it. I found a fan, but I don't know what I did with it. A lot of your fans in a computer, in fact, all the fans in a computer are brushless DC because you don't. When these things right here, these create a lot of electrical noise when it makes the switch back here on the commutator. It creates a lot of electrical noise, makes a lot of electromagnetic interference. So inside your computer, it's got so many static or electric EMI sensitive devices inside there, and all the fans inside a computer that have fans are going to be these brushless fans. So this is not a brushless motor. So it creates a lot of noise. So I could probably put my oscilloscope up on that thing and start running it. And I bet it would pick it up. this probe might not pick it up because it's shielded. That's not the motor. That's noise. I need another probe. These probes right here are shielded all the way down, and they don't pick up very noise. Yeah, this is noise. Y'all can't see that. Let me put my camera up. This is just noise from out here. Usually, Alabama Power is really bad. So usually picks up 60 cycles. So a lot of times, if we want to see if a scope probe is working, if the wires broke, we'll just come up here and we'll just touch it with our hand. Let's see, let me turn it on. And it usually picks up 60 cycles, but it's picking up something. But I don't know if you can see the lines. So that's just regular noise it's picking up. But what we're doing is we're looking at, so that's 60 cycles. So what we're doing is we're looking at this at the top. Can you see the noise it's picking up? If I get closer. So we're not talking about just the static noise. We're talking about this stuff that pops up there. Can you see it picking up all that motor? Oh, it's
I
picking.
hear a computer fan running.
No, that's this fan. This motor.
I hear that, the computer fan back there too. It sounds like
It's probably just the line. So let me turn this thing off. So that's normally 60 cycles that it picks up, which is Alabama Power. But what we're doing is we're looking at all the, so you can see DC motors are very noisy, electrically noisy. You know, see all the noise coming off of this thing. Well, if this was a brushless motor, it wouldn't do that at all. But it's that switching, when it switches across those commutator windings, or commutator slots. So this has very low maintenance. We get back to these guys, they have brushes. All these have brushes. Stepper motors, we have no problem. They'll last forever too. They don't have any brushes. But when we get back into these permanent magnet motors and these shunt motors and these series motors, and if they run a long time, if they run a lot, then you're going to have to maintain the brushes and the commutators on them. So we used to have we don't have one around here, but we used to have a little rock that had a grinding thing on it. You'd open the plate up and you'd run the motor and you'd put it down on the commutator and clean it off. You know. And then the brushes, you're going to have to place the brushes on. And that's usually, your alternator goes out in your car, that's what it usually is. The brushes. So we were going, I had a big custom van, it was beautiful. That painted on the side, those are not popular anymore. But we was going down to go shores and my alternator went out on it. And these brushes were accessible, so I popped the brushes out and one of them was wore out. And I took it to the dealership and it cost me $2. So I fixed my alternator for $2. How much does alternators cost? A lot. No, over $100. I'll let you buy one off a junkyard. So AC motors, we have single phase motors. We need to understand these are all over the place. We have capacitive start, capacitive run, split phase, and shaded pole. 3-phase, we have Y motor, YY motors, delta Y motors, delta Y motors, wound rotor motors, and synchronous motors. Synchronous motors basically use DC. Single phase motors, a rotary current is produced by induction. So what we do is we got 2 coils on the outside that now are referred to stators. What do we need to induce a voltage? We need a magnetic field, we need a conductor, and we need motion. So what's nice about AC, AC has motion built into it because when we generate an AC waveform, it goes up here, drops down, go to 0. So AC wants to induce voltage into anything, and you can see exactly here. So this scope is not hooked up to anything. The scope is not hooked up to anything. But yet when I come up here and look at it, I see what? But where's this voltage, what's my scope, where's that voltage coming from? This is being induced into this lead right here. And it's being induced into me. So I can come over here and touch the tip of this, and this is me. This is the voltage being what? Induced into me. So AC wants to induce voltage, and that's a pretty good deal, right? So this is me. Unless I'm going the wrong way. I was going the right way. So I'm getting pretty good 60 cycle too. I'm getting what? And this is going to vary. 200, about 300 millivolts worth of voltage induced into what? Into me. And this is what we usually do. When I pick up a scope, you'll probably see me touch the probe like that to see if the probe's working. And that's what I'm doing. So that's me. So if I've got motion and I've got a conductor, even though I'm not a good conductor, I'm a semiconductor, but this scope has like 10 megohms worth of opposition, so we're not going to load it down. Then AC is going to induce a voltage. So what that means is, if I've got this, if I can put a conductor into the center, and then I have AC up here, when this goes north, then this other pole would do what? Would go south, Rick. This magnetic field is coming out of this one, it would strike that one right there, so it would create a south pole, and my south would create a north pole. But the problem we have is that when this goes south, this goes north, right? You understand? So if I didn't do anything, a single phase motor would just sit there and hum at you. Because it can't move, because one of the fields is not what? Moving. So somehow we got to create a shifting field. We have two things. If you had AC, you'll understand this. If you hadn't, then we'll just talk about it. If we have capacitors and we have devices called inductors that create phase shifts. So what I can do is I can come over here and have one winding, and then I can come over here and have another, and maybe put a capacitor in series over here. And what it will do is it will cause this over here to be slightly out of phase with that over there. So that means when this right here is dropping down, this right here is going to be what? Still up here. So this magnetic field is dropping. This magnetic field's maximum in the motor would do what? It would turn. And then everything swaps around. So what this guy right here does is we call it a start winding in a single phase motor. We got to have a start winding in a single phase motor. Inductors cause phase shifts. Inductors are nothing but a bunch of coils of wire. And then capacitors are nothing but two devices. We bring two electrical plates real close together, and they electrically statically couple to each other. So the rotor current is produced by induction, no brushes or slip rings. So right off the bat, that means less maintenance, right? No brushes, no slip rings. The rotor is not wound. So all that copper that goes into the rotor, the armature on a DC motor, is not required for an AC motor. So what it means right off the bat, AC motors are going to cost a lot less per horsepower. The biggest disadvantage is we just can't control them as precisely as we can DC. So what happens is the rotor, if we looked at the rotor, if we could take it apart, you'd see these bars going through it like this. And they go at an angle. And these are conductors, and they're braided on this side. And then they go, and so this is called a squirrel cage, by the way, because it looks like the cages of rats and stuff that you can buy to run on inside your thing. So what happens is we come over here and we put an AC field. This induces a voltage into these conductor bars, which creates a magnetic field, which is going to be really strong to start off with. Really strong to start off with. Because the relative motion between the stator and the armature is big, right? So if this is 60 cycles, then that thing's going to see 60 cycles out there. But then we got to do what? For a single phase motor, we got to create a phase shift, and we're going to do that with either capacitors or inductors. So split phase motors, these create a phase shift with inductors, And then capacitive motors, of course, creates a phase shift with capacitors. So if we didn't have those devices, so you can tell when your start capacitor goes out on you, a single phase motor is just going to sit there and hum at you because it don't have the watt, it don't have the shift. Single phase motor, rotor current is produced by induction, not brushes or slip ring, requires an out of phase voltage to generate in a secondary winding called a start winding to start. Starting torque is low, easy to repair and maintain, easy to efficiency is less than a three phase. Power factor is low, and we won't talk about it in this class. Most used in domestic and small commercial applications, normally reversed by changing the connection to the start winding. So what we do is the start winding is real cheap. They don't use a lot of copper because all that's in there for is to get the motor turning. Once anything that's in motion wants to do what? Stay in motion. So what happens is the rotor itself is slightly out of phase once it starts running. So what we do on most single phase motors is there's a centrifugal switch mounted on the rotor. And what it happens is when the motor comes up to speed, it kicks out the start winding. So the start winding on most AC motors kick out instantly, real fast. If you ever hear one, you get down there and you hear that click, it's clicking out the start winding. Three-phase motors. Rotor current is produced by induction. No brushes are required. Does not require a start winding. Start torque is high. Hard to repair and maintain because now you're dealing with three phases instead of one phase. Run torque is good. Efficiency is high. Power factor is high. Normally used in industrial applications. Normally reversed by swapping two leads we call L1 and L3. Are we okay? Question? Some of y'all have already had this. So capacitive motors, good starting torque, poor speed regulation, cheaper than capacitive run motors. So what we do is we have a start winding, which they don't show. So this is the start winding, and to get current flow through this, it goes through a centrifugal switch. And then this is not right. Then we wouldn't have this. We don't have a run capacitor. So we have what they call a capacitive motor. They have a capacitive start motor, and then they have what we call a capacitive run motor. A capacitive start motor has a capacitive start motor has one capacitor, and it's just in there to get the motor what? Started.
Start.
Yeah. If it has a run capacitor, then that capacitor in there creates a better phase shift. And what a capacitive run motor still has a start winding, a start capacitor in it, but the run winding makes the motor actually can create more torque at a smaller size, but it costs a lot more money. On these motors, what you'll see is they'll have a hump on. Most of these will have a hump on the side. And that hump is just where the start capacitor is. And if you got a capacitive start and capacitive run motor, you'll have two humps on it, and one of them will be for the start capacitor, and one of them will be for the run capacitor. So the advantage of a capacitive run single phase motors is it's a smaller size. They cost more, but it's a smaller size. So you'll see these motors used where you have to mount them is limited. So all the motors in your house, like on your HVAC system, these are all capacitive motors, and we don't have any capacitive start or capacitive run motors in our house. We okay? So there's a good picture. Single capacitor start motor characteristics more expensive than split phase motors, which we hadn't talked about yet. More starting torque, 200-400% of full load current. Lower starting current, 500 to 700, 500% of full load current. See, that don't make sense. Torque, more starting torque. Workhorse of the general purpose industrial and residential motors. By the way, if you on your outside, since those motors are outside, that capacitor is exposed to a lot, and usually these guys would be harder to fix, but if you ever look at the motor, there's gonna be two brown wires coming out of it, and that's gonna run to a little box, and that's your start capacitor. So, on HVA systems, on the big outside units, odds are your motors, the capacitors are not gonna be mounted by the motor, they're gonna be mounted away from the motor. There's two brown wires, very easy to find. This would be a capacitive run motor. This is a better size to run torque ratio. So these guys, you get more torque run torque out of them. So like I said, about the only time you'll run into these is where they mount at. You're limited to the size that they mount in because they cost more money. Split phase motors, these basically deal on inductance. They work the same way. Characteristics, less expensive than capacitor motors, low horsepower, very low starting torque, high starting current, single voltage, primary use for grinders. So I've got a grinder at my house, and you turn it on, and it don't come up the speed. It starts because it don't need a lot of starting torque, right, and stuff like that. Washing machines usually use these because they compensate with a lot of gears on them. So if you see a single phase motor and it don't have a capacitor on it somewhere, then the odds are it's a split phase motor. Most of your fans, like in your freezer and everything, those are going to be split phase motors. Shaded pole motors, these are used all over the place. This is probably what's running your fan. So we've got one of these somewhere, guys. But like I said, this is not where we use these. But a split phase motor, what they do is, if you look up here, they got these shading coils up here. Can y'all see it right there? And this acts like an inductor. Can y'all see it on that picture? I need to blow it up. And what this does, it creates this little shading coil creates a slight phase shift. So here's your coil that creates the magnetic field. This creates a slight phase shift from this side down to this side, which causes the motor to spin. These are used in fans. These are used in pencil sharpeners. So if you went over there and took our electric pencil sharpener apart that's over on the other side, it would have one of these in there. And we've got one of these somewhere, but I can't find anything today. Three phase. So three phase, what we do is we have three phases. They're usually called A, B, and C, or like L1, L2, L3. What happens though is these guys are generated 120 electric degrees apart. So this was phase A, and this right here was phase B, and then the other one was phase C. And then if I kept going, they'd look like that. Well, these things make great for making DC power supplies out of them. You can let very little filtering. But you're looking, when A comes up, when it starts down, B is coming up, then C is coming up. So what happens is A is big, when it drops down, B comes up, C comes up, A, B, C. So what this does is it creates a field without any capacitor that automatically does what? Moves around the outside. So three-phase motors don't have to have start capacitors. And to reverse, by the way, on a single-phase motor, you can reverse this one. This was we were over in Japan, and this was the motor that they had on our clock in our shop. It had a little shaded pole motor on there. So you had to set the clock all the time. But what you have to do on this one is to reverse this, you actually have to pull it apart, take off the stator, turn it around, and put it back on there, and then this will run backwards. So we did that on ours, and we put all the numbers on our clock backwards. So instead of going 1, 2, 3, 4 this way, ours went 1, 2, 3, 4 this way. You know, people would come in and they would look at it. But on a single phase motor, what you do on a single phase motor is you swap this winding, and start winding. If you swap both of them, the motor runs in the same direction. So we normally start the start winding because one reason it's got less current flow through it and it's only in the circuit for a short amount of time. If you swap both of them, the motor will run in the same direction. So some motors, this is reversible. It'll have a plate on the back of it that you can pop off and you can actually swap the start windings on it. So single phase motors, we reverse those by, most single phase motors, we reverse those by the start winding. This we would actually have to tear the motor apart and put it back together to make it run. What we do on a 3-phase motor is we just change any 2 leads. So no matter how I change them, then let's say B occurs first. I go B, C, A, B, C, A, B, C, A. If you look at it, it's going what? No, that's right, wrong. B, it would be B, yeah, and then it would be C, and it would be A, B, C, A. Is that right? Let's swap this one. This one. That would be B, C, A, yeah. So we look, it goes, here it's going A, B, C. Over here it's going C. No, this is wrong, Rick. It's supposed to go C, B, A. So which one did we swap? This one and this one. So I go B, C, A. Is that what I'm doing? B, C, A, yeah. So this would cause it to rotate backwards. Or if we swap A and C, then it would go what? It would go C, B, A, C, B, A, C, B, A, and that would cause it to reverse. So what we have to do to reverse a 3-phase motor is we can reverse any 2 leads. The industry standard, and this is what you need to learn, is the industry standard is to swap L1 and L3. So if we call our phases L1, L2, and L3, then what we would do to swap it is we wouldn't swap 2 and we'd swap 1 and 3. And that's the industry standard way. Even though any way would do it, you want to do it according to the way the industry does it, right? You understand? So that means you go out there and you look at a motor, you know what to expect. So this is showing the phases. This is showing the power. So this is the actual power curve. This is really cool. So you can actually see the what? You can actually see it what? Moving, which is pretty neat. Synchronous motors, what we do with synchronous motors is we put a DC. So what happens, the speed of a motor, so the speed of the motor is set by, anybody know the for an AC motor, anybody know the formula for the speed of the motor? You can see it different ways. The way I learned it was 120 times the frequency divided by the number of poles. So it means if I come over here and do this, and this was north and south, then that would be a 2-pole motor. It takes, for 2 poles, this would this would give us, or you can say 60 times the frequency divided by pole pairs. So if I take the frequency and divide it by the number of poles, that would give me my revolutions per second. But what we're trying to do is get our revolutions per minute, right? So that's where this formula right here came from. The problem is that most motors are not rated by poles, pole pairs, they're rated by the number of poles. So this would be a 2-pole motor. So if I had a 2-pole motor running at 60 cycles, how fast would it try to run? Well, that's the calculator. If I had a 2-pole motor, which is this is the minimum we can have, is 2 poles, north and south, and I'm running it at 60, I'm running it at Alabama Power, which is 60 cycles. So it'd be 120 times 60 divided by 2. So what would the motor try to run at?
3,600 RPM.
Yeah, 3,600 RPM. Now, the way this thing works is that we're inducing the voltage into the rotor, and we've got to have motion. So we start off up here, I'm putting 60 cycles on my pole pieces. 60 cycles. Well, the motor starts rotating. So let's say we're putting 60 cycles per second. The motor starts rotating. Well, now what it's doing is it's getting up to speed with the field. So we start off with 60, and then this guy here is rotating at 0. So the relative motion would be 60. The motor gets up to 1 RPM, and that was going to be 60 or 1. That'd be 60, this would be 59. You'll follow that. So now the current in the armature or the current in the rotor is going to start going down because we have less relative motion. So as the speed of the rotor starts coming up, the relative motion between the two goes down, which is what we wanted to do. So we want a lot of starting torque, but what we want is we want the motor to be able to run the load. So the frequency, the speed of the rotor is this. It's 120 times the frequency minus what we call slip. So there's got to be some slip in the motor to keep current in. There's got to be some slip in the motor to keep current flow in the rotor to cause the thing to create the torque to run the load. So you might have a 4-pole motor. What would be the field speed of a 4-pole motor? So what you're doing is you're calculating the field speed. This is not the rotor speed. This is the field speed. My brain would do. So this would be the field speed. So what would be for 4-pole motor? That's going to be what? 120 times 60, right? Divided by 4. So what we do is we'd put 2 poles over here now, and this would be a 4-pole motor. So this guy here actually makes. So what would the speed be? Well, if you look at the motor, it's probably going to be rated like 1725. Because it's got to have slip, an induction motor's got to have slip so it has relative motion to induce current into the rotor. So on an induction motor, the rotational speed of the rotor will always have to be less than the field speed. Because if they locked in there together, so if they both was moving at the same speed, we'd have no relative motion. So this guy here's got to always move a little faster than this guy, so you keep up, so you have that induced motion. Does that make sense? By the way, they call this, and that's what the motor's going to be. The rating on the motor is going to be RPM, and that gives you the speed of the motor if you're running it at its rated horsepower. If you're running lower than its rated horsepower, then the motor's going to run a little faster than 1725. If you try to run it above it, then it won't run above it and create the horsepower. If you try to make it create more horsepower, you could stall the motor. On a synchronous motor, we're not dependent on induction to run the rotor. So what we do is we come up here and we bring a magnetic field into the rotor. So this guy's going to have slip rings on it, not commutators. And now we don't depend on induced voltage. So these guys here will run at fill speed. So if I had a 4-pole synchronous motor, it would run at 1800 RPM. Did we see many of these? No. US Steel had them out. They had good gracious, it was like a 3,000 horsepower synchronous motor, but they were using it for power factor correction, and I'm not going to explain that. So you'll run into these, but not very often. DC motors, very easy to control. Control speed of induction AC motors. Speed is not normally controlled with voltage. If voltage is lowered, both speed and torque decreases. If voltage is increased above the rated voltage, torque increases, but speed does not. What are we doing here? Okay, this is what we're talking about. So on a DC motor, what we do is we just control the voltage going to the armature if it's a regular shunt motor. And if we put more voltage on it, speed goes up. If you put less voltage on it, speed goes down. On an AC motor, it looks like we could run it with frequency. So, but if you got a ceiling fan, what you're doing is you're switching poles. So you start off with so many poles, you flip a switch, and it'll either add them. If it adds more, it'll slow down. So that's what you're doing with your switch on there. If we try to control it, it looks like we can control it. We can't change it. So on your ceiling fan, you're changing the number of poles. So normally these are going to be motors they're going to have set speeds, like a 3-speed motor or a 2-speed motor. These are probably going to be controlled by changing the number of poles. So if the number of poles goes up, the speed comes down. So if you ever took the switch apart on a ceiling fan, you'll see it's got one wire coming in, got 3 wires coming out, and each one of them is going to select a different number of poles. So why can't we control it with frequency? We can control it with poles, but that would be in certain speeds, like a 3-speed motor or a 2-speed motor. But what if I wanted to constantly control the speed of an AC motor? It looks like we can do what? It looks like we can control it with frequency. Unfortunately, this is what they call them. They call them variable frequency drives, if y'all have ever heard that term. But we can't do that. The problem we have is this formula right here. The amount of opposition to AC those coils of wires have is set by a formula called 2 pi FL. 2 pi, of course, is a constant. The L is built into the motor. But the problem is, if I raise the frequency, what happens to the opposition of the motor since it's on top? The opposition goes up. So the problem we have here, if I raise the frequency, enough current is not flowing through the stator, and the motor won't create the torque, and it'll stall. If you lower the frequency, X of L goes down, and the torque of the motor, the speed will go down, but the torque of the motor goes up. And you wouldn't want that. Normally, we want, if we're going to pull a certain amount of torque, we want to do torque. So the way a variable, so it says, X of L is opposition to AC voltage caused by coils of wire in ohms. F is the frequency, L is the inductance of the coils of the wire measured in henries. The amount of inductance depends on how many factors. If the frequency of an AC motor is changed, the opposition to the AC changes. If frequency goes up, opposition goes up, and of course torque goes down. If frequency goes down, opposition goes down, and torque goes up. We don't want it to do that. We want it to produce enough torque to run the load. To control the speed without changing the torque, requires both the voltage and frequency to change proportionally to the same direction. So actually, to control these things, if you got a variable speed drive, what it's actually doing is frequency goes up, voltage goes up, if frequency goes down, voltage goes down. And they run them exactly the same. And what they do is they just take the voltage the motor's rated at, they divide it by the frequency, and that gives them what they call a volts per hertz. So if you ever get the opportunity to program a variable speed drive for an AC motor, that's something you got to enter in there. You got to enter the voltage the motor's designed to run off of, and the frequency it's designed to run at. And then the electronics in the variable speed drive will take care. I call it a variable speed drive, but most people call them variable frequency drives. But on an AC motor, you can't control the speed by just controlling the frequency. You got to control the frequency and the voltage. So if you double the frequency, you double the voltage, the motor will run fine. Yeah, if you're going to control it if you're going to try to control the speed of an AC motor. So I can't control it with frequency because frequency, this is set by the coils of the motor. So if you don't rewire the motor, if frequency goes up, its opposition to current goes up. Which means now your stator is not getting the current required to produce the torque. So the motor would stall. It would stall on you. If you lower it down, torque goes up. So now it's trying to produce more torque than what's required, and it will tear stuff up. It would tear your gearboxes up, and it would tear stuff up. It's not trying to produce the torque needed for the load. It's trying to produce more torque than what's needed by the load. So what we do is the variable frequency drives, they're not only changing the frequency, they're also changing the voltage. So they want to run at RPM. They start dropping the frequency, they drop that voltage down. So if it's 1 volt per hertz, then that's what you would run it at. You could actually control the speed very precisely. And what's nice about this is that if I'm going to control the speed of a DC motor, I'm going to have a DC drive. If I'm going to control the speed of an AC motor, then I need an AC drive, electronic drive. These guys here cost about the same money. So what are you saving? You're saving money on your motor. So now, if I'm going to control the speed, odds are they're going to be AC motors. And what advantage does an AC motor have over a DC motor? It costs a lot less per horsepower, a lot less. Because you don't have to have all that wire. So a DC motor, big shunt motor, you got all this copper wire out here in the armature. The field. You got all this copper wire in the rotor, and then you got the maintenance you got to do. On an AC motor, you got the copper wire in the stator. You have no copper wire in the rotor, just bars. They use aluminum bars. So AC motors are a lot less expensive. DC motors cost a lot. So if the drives cost the same, and I can control this speed, I just don't have the precise control that I have with DC, but these are good enough, then by George, I'm going to use an AC motor. So when I was at US Steel, we had tons of DC motors because they wanted to control the speed. Now if you go someplace, they're going to have AC motors because they're so much cheaper. So this is kind of like a variable frequency drive. This is a real good animation. So basically they're using pulse width modulation, guys. The same thing we do on DC, but they're doing negatives and positives. And the motor actually averages this out. So if I change the duty cycle, the voltage would go up. If I make these shorter, then the duty cycle would go up. And if I bring them closer together, then the frequency would go up. So this is a good animation. I think that's it. Yeah, this is showing changing the voltage with the pulse width modulation for AC. So this is what the motor would see. The motor would see it as AC, but that's what the actual electronics do. And turning it off and turning it on, produce means the devices that control it, don't get as hot. Well, that's motors. Got any questions? Okay, guys. Group one, you can split. So Sarah, you can split.